everybody. My name is Marcus Meyer, and I'm a product marketing manager with STMicroelectronics, responsible for MCU, MPU, and AI. Together with my colleague Louis GOBIN, who is an FAE for our AI activities, we want to provide an overview about the NanoEdge AI Studio software package. AI can be a complex process if companies have not prepared their path and validated how it will transform their offerings. STMicroelectronics has built the most comprehensive approach to support customers in this process. This is what we would like to discuss with you today. The good news for ST customers is that STMicroelectronics recently acquired Cartesiam, a software company exclusively focused to help developers to easily, quickly, and affordably create smart objects without AI skills. This acquisition positions STMicroelectronics as the world leader in embedded intelligence on microcontrollers. Over time, devices have evolved from standalone products with a basic functionality to connected products with mainly reporting capabilities, and then smart products but relying on remote cloud-based intelligence. This last implementation requires a significant and costly infrastructure, security challenges, and not to mention the privacy aspect of sending data to the cloud. Technological innovation now allows intelligence to be embedded directly into devices closer to where the signal becomes data. As we saw on the previous slide, the era of standalone products is over, and even connected products no longer provide enough value to the user. Today, customers not only want to know when there is a problem, but they also need valuable insights to make thorough decisions. For example, the washing machine needs to be serviced, and it's probably a belt problem. Or an abnormal glass breakage noise has been detected and the alarm siren should be triggered. What if you could easily enhance your product by simply adding EdgeAI capabilities that run in your STM32 MCU, taking your products into the next era? The issue is that creating EdgeAI devices usually comes with extraordinary challenges. For example, there are no qualified datasets available, there's a lack of data science resources, a strong cloud dependency, and also significant upfront investments. All of these challenges combined make projects so complex to tackle that few companies have actually started on the subject and even have products in the market. ST's approach to machine learning consists of providing the NanoEdge AI Studio, a PC-based push-button development studio for developers that runs on Windows or Linux. One of the big advantages of using NanoEdge AI Studio is that no specific data science skills are required. The developers can be up and running today, and using the studio, any software developer with absolutely no AI skills can create a self-learning engine in the form of a machine learning library, which will learn directly on the device. Once the library is created, it can be pushed into the microcontroller to train and infer directly on the device. Two types of libraries can be created with the studio: an anomaly detection library as well as a classification library. The generated code can run on any of our over 1,500 part numbers of the STM32 family, from our low-cost devices with Cortex M0 core up to high-performance devices with the Cortex M7 core. Now, Louis will show you an example how easy, simple, and straightforward this process is.
Thank you, Marcus. So, as Marcus mentioned, NanoEdge AI Studio has two main types of algorithm available right now. The first one will be anomaly detection. So this class of algorithm really aims to be able to adapt and learn at the edge with really no other resources or connection than the microcontroller it's running on. So to find the right algorithm, we'll need some sample data for our use case that will be fed into NanoEdge AI Studio. This does not need to be an exhaustive training dataset, that it's not used to train the algorithm, but just characterize the use case and select the best algorithm for that use case. Once we have selected the algorithm on our computer, we can include it into our product. At this point, the algorithm is still untrained. And once it's all on its microcontroller and set up in its working environment, it can start learning what this nominal state of the environment is. And then after that period of unsupervised training, be able to detect and report the anomalies when they occur in real time. Our second type of algorithm is more conventional and focuses on classification. So due to the nature of classification use cases, the model needs to be trained beforehand in NanoEdge AI Studio. So all the training data will be loaded into NanoEdge AI Studio, and you will obtain at the end of the process a fully trained classification algorithm ready to classify events. So it's a different algorithm class for a different type of needs. And really, it doesn't make sense to train classification at the edge, because you would need someone next to every device deployed to be able to say this is class 1, 2, or 3. So this is why we have that training step now moved back to the computer in NanoEdge AI Studio itself. Of course, multiple NanoEdge AI Studio libraries can run on the same MCU at the same time. So this lets you have collaboration between multiple algorithms, either for unrelated tasks, or you can have algorithms collaborate between them. So adopt the flexibility of anomaly detection that can filter out and weed out the 95, 99% of detection events, which are nominal. And then when there is an anomaly, pass the data on to the classifier that just has to handle the differentiation between different types of anomalies. So you still get the insight of classification with a much smaller data collection campaign, a much smaller footprint on the end device, and a more reactive overall solution as it adapts to the environment. NanoEdge AI Studio first characteristic really is that it's sensor agnostic. We do not need to know where your data come from, if it's from one sensor, a combination of sensors, or even if it's pre-processed already. If you already have knowledge on your use case, that can be the case. However, this makes the possible use case and application kind of vague and so large that we found the need, both with our clients and with ourselves, to have some reference to show what has been done and what can be done with NanoEdge AI Studio to inspire new use cases and new applications. So on the left side of this slide, you can see the sensor that we've seen the most use out of: vibrations or accelerometers, pressure sensors, volatile organic compounds detection, current, magnetism, and sound are really the main ones that we've seen current use case for. So on the right side, however, we have something more concrete, and we have that on the website data.cartesiam.ai, where we list data sets and use cases for those examples. Some of them are rooted in very practical and very real products already existing and deployed with NanoEdge AI Studio. Other are from reference dataset from the machine learning community to be able maybe to compare NanoEdge AI Studio to other solutions out there. And finally, we have use cases that we either just found interesting, even if they don't have a real world application yet, or they're use cases that we have just found fun or interesting in another way, such as beer detection. So for today's demonstration, we will be using STMicroelectronics new time-of-flight sensor, the VL53L5CX. The standard use and the values returned by a time-of-flight sensor are an array of distances to a background, an object, and environment. Depending on your use case, you can use these measures to detect activity, just to detect a presence, or even to draw out shapes of something. On the other hand, we have the problem of identifying materials that everyday objects are made of. The most obvious use case for that would be recycling, for example, being able to say that this object is made of that material. And it's actually a fairly hard problem. One way to solve it, we've seen existing today, is to train a camera or a set of cameras to recognize an object, then match an object to a database based on what it looks like, and then in that database, identify what that object could be made out of, or hopefully is made out of. So quite a lengthy process that requires a lot of training and a pretty complex end implementation. So in this demonstration, we'll show how EdgeAI can bring a cheaper and more efficient solution to edge analysis use cases, such as being able to detect the material an object is made of. We'll be using the very same time-of-flight sensor, and we'll be using the luminosity return instead of the distance directly. So it's slight alteration on its intended use. It's an interesting potential use case for time-of-flight sensor, as it's meant to be an example of a cheaper and faster solution for the same problem, in that case, material identification. So in this demonstration, we will use this time-of-flight sensor to log the luminosity returned by the sensor array to the sensor array, and send it to the computer that you will then see on screen. From there, we'll collect the data, create an algorithm in NanoEdge AI Studio, as presented in the demonstration following. On the left of this video, there is a setup we are going to be using to collect data. There is a frame holding up the sensor that we are going to be using today, time-of-flight VL53L5CX. On the right of this video, we see NanoEdge AI Studio, the welcome host screen that you would get once you start. On this welcome page, we can now create a new project. So we're going to select which algorithm we want to use. We have anomaly detection available and classification, and this use case is addressed to classification. Then you can input the name and description of your project, as well as a target platform. So any Cortex-M will do, M0 to M7 included. And then you can also allocate the maximum amount of RAM you want your algorithm to fit in. Same thing for the flash. This step might be a bit backward to the usual machine learning at the edge development pipeline, but we felt that it's a tool for professional use cases and for deployment at the end. And it makes sense to only consider the most relevant results. Having the perfect models, but that just don't fit on your platform is meaningless. When running NanoEdge AI Studio, we aim to give you the answer to, is this going to work for my product? This is not an answer that can be restricted to model performances. It also needs to include the platform and the footprint. And if any of those is out of bound, it doesn't work. Finally, you choose a sensor you're going to be using. So here we have listed the most common sensors used by the platform, but NanoEdge AI Studio being sensor agnostic, we can just select the number of axes we're going to be using, in that case 1, and move on. So now we're going to be importing the data for our training testing sets. So we could import data from a file if we had files of the data. For the current example, we will get directly the data from the serial port. So we can select the port, the baud rate, the number of signals which to collect for this class. And we're going to get the data on our first object, in this case, a paper napkin. And we want to collect about 100 signals on it. In a signal, each row represents multiple data points. They can be over time or over space. So in this current case of time-of-flight sensor, since we collect the whole array of 64 section in one signal, it's over space. And then we're going to have a small speed up, and that's going to be recurrent during the data collection time, so we don't take too much time on those. Overall, the data collection took about 20 minutes. So we're going to pause the sampling now to change the position of the napkin, just to get some variety in the data. And then we're going to move on to a sheet of paper. So get more, to get different data for our class that's going to be paper. So now that we have all our data for our first class, we're going to name it. And at the same time, we're going to create a second class. So that's going to be the class objects. So we're going to sample also from a set of objects, in that case, a glass container and a glass in different configurations. And now, finally, we're going to create and sample for our final class, plastics. So we're now done with the data collection, and we'll move on to finding and training the best algorithm for that use case. So in this step, the computer will be doing the heavy lifting. So we're going to launch a search for the best algorithm for our use case, and we want to include all the classes, of course, in that search. So your screen is going to be divided roughly into left and right. On the left, you can see the metrics that we're going to be using: balance accuracy, confidence, RAM, and flash. And underneath, there is a graph representing visually how the classification algorithm currently selected is performing. On the right, you can see the historical performances and weight of the best performing algorithm through time, basically, so how the search is moving along. To come back to the metrics, balanced accuracy is used to measure the performance of the model. It is used to simply measure if the model is able to assign the right class to data points from the testing set. As we observed that for most use cases, one or more classes are just underrepresented. And this metrics take that imbalance between classes into account. So it's really just a measure of the model's performance. And as you're probably going to have classes that are overrepresented or underrepresented to one another, it allows you to cope with that and have the evaluation of the model in one simple number. The second main metric we have is confidence. If balance accuracy is bad, confidence doesn't matter, but confidence can let you differentiate between two models that have the same balance accuracy and is a pretty useful measure. It's basically a measure of the functional margin, and it is used to make the model as resilient as possible. These metrics basically look at the distance that the model is able to put between the data from different classes in its representation of that data. And as we know, lab data will never be able to account for all real-life use cases, such as the data we fed into the classifier that we have here. And this metric is here to help you select the model that can best cope with the unknown of the real world and real world applications. And the flash, as well as the RAM, are the footprints of the currently selected model. They will always be within the envelope indicated in step 1, but for two equivalent models, we will select the one with the smaller footprint by default. And once we're satisfied with the results, we can stop the search and move on to the emulator. The emulator is available in NanoEdge AI Studio, but you can also use it through the command line interface if it's preferred. So it will emulate the Cartesiam we selected in step 1 to test the algorithm selected in the previous step. This lets you run tests without having to implement on the board, as well as use test files if you have them, especially to testing edge cases in a reproducible manner. An option we will not be using today, but is relevant for a lot of use cases, is the ability to run multiple verification in sequence. So here, if we put the number at 2 instead of 1, we will need 2 consecutive detection of the same class for that result to be returned by the emulator. This greatly increases the certainty of the model against an event, and it can be a very powerful boost to your algorithms. Once again, it's not for every single use cases, but a large part of the use cases out there can use this, and it's a very easy and straightforward way for boosting your result, and this is just a tool to be able to test it in the emulator. So after we initialize the emulator, we can see that it starts detecting the plastic of the table itself, which would be expected behavior. It's then going to properly classify the paper napkin and the sheet of paper, as well as plastic and glass elements that were present in the training set. However, we also want to see if it works with elements that were not present in the training set. So we're going to show it a couple of things to test whether or not it will be able to identify them. So in the first case, we have just a plastic stance presented to it, which is properly detected as plastic. And secondly, the screen of a smartphone, which is detected as glass as well, so properly classified. This is a small test session, but the idea of the emulator really is to let you test live just after you found an algorithm, after you've inputted your data, training, testing data, assess it on unseen data before, especially on edge cases that you know you're going to encounter if you have that data available. It's also a good way to just plug in your sensor to your computer and be able to see what's going to happen when you move around in the environment, if that's the type of use case you're studying. Finally, you can test your algorithm on your board by clicking on the compile button in the last step, which will let you download the zip file containing the compiled C library as a .a and 2 header files that go with the classification library, as well as some documentation. To actually interact with the library from inside your code, you're going to have 2 main functions, which are initialize and detect. It really does what it says, but for the detect function, you would feed it a signal, and you could get out either the class that it most likely is, or the likelihood for every classes for that sample. And from there, you can either implement a different logic, you can do double checks, or you can simply use the result and return it or act upon it.
As you have seen in the presentation and the video, the NanoEdge AI Studio is a powerful solution which allows you to bring artificial intelligence to the edge running on cost-effective MCUs. It runs completely autonomous at the edge with no cloud connection needed, which provides privacy, data security, and optimizes the latency. It helps developers to bring such a solution quickly to the market without any previous knowledge in AI and data science. It works on all of our over 1,500 STM32 microcontrollers, from low-cost ARM Cortex-M0 up to high-performance ARM Cortex-M7 based products. Okay, so if you are interested and want to get started, please send us an email to edge.ai@st.com. Thanks again for joining us today and have a good day.